The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Welcome to the tutorial on the method of simulated moments. Collaborating together on this tutorial is Armin Ashori, Ross Collins, and Ali Camille. We will present the tutorial in two parts. The first part, presented by me, Ross Collins, is an overview of the MSM, why it's useful, and how it works. The second part, presented by Armin Ashori, will go through the details of how to implement the MSM in Bentson DSS. Background information on the MSM is included in the associated book chapter with this video. The chapter goes into much more mathematical detail on the MSM formulation, which the interested viewer should consult if looking for more information. In this video, we do not dissect every individual formula, but instead try to give a useful overview of the MSM and then apply it to a simple example. The step-by-step replication of the tutorial will likely require reading and understanding the book chapter in more detail. Still, this video should give a flavor of why MSM is useful, how it works at a general level, and what sort of time and effort is required to implement it in system dynamics models. So what does the MSM let you do? Well, according to this quote, it allows one to compare time series data against the same variables in a model and minimize the weighted sum of a function of the error term by changing the uncertain parameters until best fitting estimates are found through optimization. This is important for model validation. So specifically what MSM does is it compares the moments of real data against the moments of simulated data, or just the model output from a simulation. So moments are things like mean, variance, skewness, kurtosis is another one. These are the first, second, third, and fourth moments respectively. An important thing to realize is that unknown parameters in a model will alter the simulated moments. So if you have some unknown parameter x and some moment y, if you change x, then y will change. So what the optimization method does, referred to in the quote up at the top, is it will find values for our unknown parameters that minimize the weighted difference, and I'll get to why weighted is important later, the weighted difference between real and simulated moments. And these weighted differences are called the error terms. So we're going to apply this MSM to a simple obesity model. We basically have weight data in Excel. This Excel file is included with this video. We have weight data for a population of 1,000 individuals at 5 different points in time, specifically years 1, 5, 10, 15, and 20. The moment conditions we use are mean and standard deviation, and given that we have 5 years of data and 2 moments, we have 10 moments in total. So the unknown parameters that we're trying to estimate through the MSM technique are called overfeeding, starvation, and energy intake extra trend. So I want to show this model really quick. It's a very simple model that tracks the weight gain of 1,000 individuals. You can see you have the stock structure here, an array of 1,000 people, so we're utilizing subscripts to denote these 1,000 individuals. And the major feedback is that as weight change accrues, you have some energy intake balance that changes. This feeds back into one's energy intake through these starvation and overfeed parameters, and then alters the weight change. So the 3 uncertain parameters are here. We have an underlying trend in energy intake that impacts the weight trajectory of each individual. And then we have these starvation and overfeed parameters that impact this major feedback. If energy intake balance is on the heavier side, starvation kicks in with some parameter force. If we're on the lower side, the overfeed parameter kicks in with some amount of force. So let's see. If we click on the weight here and show a graph, we're only going to get to show the 16 of the individuals, but you can see the trajectory of them through time over the 20 years. The initial conditions are captured here. The mean of individuals is 80 kilograms, so you can see it's sort of circled around there. And the standard deviation is 5 kilograms, which is why the initial conditions differ. But you can see the trajectories, and we have this for 1,000 individuals. So then the idea of the MSM is you have these 1,000 trajectories, and you have the moments that that define these trajectories, and we compare that against the real data that we have in the exercise. So let's see, final slide that I'm going to talk about before I hand it off to Armin to go into the Bentson implementation. So basically there are four overarching steps and 4 Bentson models associated to each step. So in the first step, we are basically making the first cut at estimating these 3 unknown parameters. And to do that, we need, and I'm going to pull up the book chapter here, we need to minimize the minimize the weighted differences of these parameters. And that's what you can see here in equation 3 in the book chapter. This theta hat is the set of parameters, in our case just 3, and we want to minimize the difference between simulated moments and the real moments. D is for data. And we have here in the middle this W, which is a weighting matrix. And the purpose of the weighting matrix is to give less weight to really noisy and uncertain moments, since those are going to sort of hijack the optimization process when trying to choose parameters. So the first W that we use in the first step is essentially just taking the real data moments and squaring them and then taking the reciprocal. And those are along the diagonal elements of W. Armin will go into more detail about that, but that's our initial starting point for W. So the output of that are an initial set of parameter estimates. Not necessarily optimized, but certainly informed by this initial weighting matrix. The second step is to calculate essentially a more efficiently weighted W, or what we call W star. And it uses an algorithm that is discussed in the chapter. It's equation 4 down here. As you can see, it's reasonably complicated and requires first calculating the variance-covariance matrix of the simulated moments, which again we can do in Bentson, even though it's easier in MATLAB. And W star is simply the inverse of this matrix. So once we've got W star, we basically go into the second step, which is very similar to the first step. It's an optimization yet again, but now we have a more efficiently weighted W. And that gives us a better set of optimized parameters. An important thing to note is that we can iterate if we are not happy with W. But the final step involves calculating confidence intervals for each of our uncertain parameters. Again, in our case, we have 3 of them. So these confidence intervals are just like other confidence intervals in statistical exercises. We want those bounds to be as tight as possible, and we don't want them to include 0. So that is the overview of the MSM. I'm going to hand it off now to Armin, who is going to go through the steps, go through the major steps actually implemented in Bentson. So thank you for listening.
In each model, we have a part that captures the moments we need for the MSM process. So here, for example, in the first step model, we see that we have the main model of obesity, and here we have a part that tries to capture the moments, different moments that we have. For example, here we want to catch the mean of body weights and also standard deviation of body weights. Simply, this part tries to create like a matrix of moments, in which we for each column we have 1 simulation. So here, for example, we have like 10 simulation, and for each rows we have one of our moments. Here, since we have like 5 years of data, which are year 1, 5, 10, 15, and 20, and we use 2 moments which are mean and standard deviation. We have like 10 rows that for the first 5 years we have first 5 rows we have like the mean of our years, and for the second 5 rows we have like a standard deviation of our years. So we can create this matrix in whatever way you want, but here we try to capture these moments and create that matrix using a stack and flow system. In the first step moment, we try to find 3 unknown parameters of obesity model, which are extra trend, starvation, and overfeed. We use formula 5 in the book chapter and try to optimize those parameters based on that formula. So here in formula 5, you see like different parameters we have. For example, M of S is the average, of simulated vectors of moments. So for example, in our example, we have like 10 simulation for each one of those moments. So we average the moments over those simulation and create like a vector, which is m of s here, and m of d is the real moments values in that vector that we capture from the real data we have. W here is the initial value for the weights, and for the initial value we use the formula 1 over moments, real moments to the power of 2. In the model we call the function here as the error term. So here in the view 2 of our first step model, we can see that we have like our 3 unknown parameters here. We put them all together in one vector here called parameters, so that we can deal with them easily. So from the obesity model, we get the moments that we need here. So if you take a look at the moments here, we have the moments we have here in the last year, the year 20, you will see that we have like a matrices that has 10 moments in it, and for each moment we have like 10 simulations. So we have like a 10 in 10 matrix for each moments in each simulation. So we get those values, and here we get an average over those 10 simulation, and we create the m of s that we talked about here. So using that and using the data, the real data that we have, we calculate the difference between the simulated moments and the real moments. And here you see that we calculate the W based on the formula we have for the initial value, which is 1 over real moments to the power of 2. And using these data, we calculate the error terms here, which we just calculated for the last for the last time of the simulation, which is the year 20. So as you can see here, this formula here is the formula 5 from the chapter book that we have. And finally, we have to do some optimization on the model to get the values. So here you will see that we have we want to optimize over the error terms, and we want to minimize it. So we put the error term here and weight -1. You have to choose the policy for this optimization. So, and we want to optimize over the parameters. So we have to choose the parameters as the variable we want to optimize, and then we do the optimization, and you will get the values we need. So we do the optimization, and it may take for a while, maybe like 20 or 30 minutes. So we are fast forwarding to the values we have at the end of the simulation, at the end of the. So as you can see here, we have to like the optimize parameters, optimize values for our parameters, which are kind of close to the real values that we have. So in the next model, which is the CalcW model, we try to calculate the weight we need for the MSM process using other models. So here we import optimized unknown parameters from the previous model, which is the first step model, to CalcW model. Then we calculate a variable called S using the formula 4 in the book chapter that you can see it over here. And the inverse of that S variable is the weight that we need for our MSM process. In the first view of CalcW model, everything is the same as the previous model. In the second view, we try to calculate the S based on the formula we have in the book chapter. So here you can see that we try to calculate the average of simulated moments, and this is exactly the same as the previous model, and we try to calculate the average of each moment over like 10 simulations. And after that, you can see that that average of simulated moments here in the formula 4, and we have to subtract the real value of moments from that average, and then multiply to its transpose and get another average over that. So here we, in the moments differences variable, we try to calculate the formula we have in the book chapter, formula 4. And using that, we just calculate the S hat for the final time of simulation. We only need to calculate the value of S just for one time, and after that, by inversing the value of the matrix S, we can get the value of matrix W that we need the MSM process. So we just run the model for one time, and here after the simulation ends, you can see the value of S hat we need in the final time of simulation here. So we have like n 10 by 10 matrix that has like different moments in it, and we have to inverse this matrix to get the real weight matrix that we need. In the next model, which is the second step model, we again want to find the unknown parameters that we have using some optimization, this time using the calculated W from the previous part in the calc W part. So we import the S matrix from the previous part, and by inversing that S matrix, we get the W that we need. And also, we can import the optimized parameters from the first step model, or we can just use some random values as the initial values of the parameters. And so finally, we do another optimization to find our 3 unknown parameters, and we again use the formula 5. Just this time, we have the W that calculated from the previous model, which was the calc W model. So here in the second step model, in the view 1, you can see everything is the same as the 2 previous model. And the view 2, you can see the only thing that difference from the first step model is that we import the value of S and then inverse it to calculate the W instead of calculating W based on the data moments of that we have. Here we have some kind of a bug in Bentson, and if you try to import the values of S hats from previous model using like some kind of function like get VDF constant or any other function that tries to import the values from the previous model, then my Bentson cannot calculate the inverse of that matrix right. So here we just copy pasted the values of the calculated S matrix from previous model and just put it here as like exogenous variable, and then we calculate the inverse of my matrix instead of just using the imported values from the previous model. For the second step model, again we have to optimize the parameters. So again we have like the same system as the first step model. We try to minimize the error terms, and we are trying to optimize the parameters. After like the simulation may take like an hour or so. So after the simulation ends, we have like the optimized value for our unknown parameters. After optimization finished, you can see the optimized parameters value here. So we get like these values for each one of these parameters, and you can see, for example, 0.002 is for the extra trend, and 0.35 is for starvation, and 0.13 is for the overfit parameters here. Next model, which is the confidence interval model, we try to calculate the confidence interval of our unknown parameters. So here we need to import the optimized parameters from the second step model and the W from the calc W model, and then we calculate the confidence interval first by calculating a variable called Q. You can see the formula for calculating the Q here. Then using that Q, we calculate the confidence interval using this formula that you can see here. We have to add and decrease some values from each parameters. So here the confidence level factor, for example, for 95% confidence interval, assuming we have like normal distribution, is 1.96. Then we have to multiply that value, that confidence level factor, to square root of q and add it and subtract it from the parameters. So after that we have the confidence interval for each one of our parameters. So here in the confidence interval model, you can see that again we calculate the average simulated moment and we get the S from the previous part. Also, we have to import the value of parameters from the previous model, which was the second step model. So we get the optimized parameters here, we get the value of S here. And here we try to calculate the confidence interval using the formula that we have. So here in the formula 7, you can see that we have like 1 plus 1 over k. K here is the number of simulation. So for example, we had like 10 simulation. Then we have delta and s minus 1, which is the w, and again delta. Delta here is the change in moments of a parameter by changing the parameter for like epsilon or theta value. So for example, if we add like 0.001 to an optimized value of a starvation, how much its average simulated means may change, or standard deviation may change, the two moments that we have. So we try to calculate that delta here using some param sense variable. In param sense variable, we just add and decrease a value of epsilon to each parameters, and then we get the delta here. So using these values, using this system that you can see here, we calculate the confidence interval we need. So again, we need to run the model only for one time, and just by running the model just for one time, we can calculate the confidence interval that we need. So after running the model, you can see that we have the confidence intervals for example, upper bound confidence interval for each one of the parameters here, and the lower bound of confidence interval for each one of the parameters that we have in here. The base obesity model and the the capturing moment structure that we have in all four models are kind of the same, except for the last model, which is the confidence interval model. We have to add one other subscript that is for sensitivity analysis. For each one of the parameters, we have like one upper bound and one lower bound, so we have to add like 6 subscripts to the model, and for each one of subscript we have to run a simulation to for example, catch the upper bound of one of the parameters or catch the lower bound of the parameters. So we have to change the model in a way that it runs a simulation for each one of those subscription. But everything else is the same in our 4 models for the base of the obesity model and the moment capturing model structure. Finally, we put aside the bug in Bentson and assume that we can just import and export SAT between models and calculate the inverse of matrix without any problem. We can create just one command script that runs our sequential models and just import and export the data between them, and after like running all the models and processes that we need, just gives us like the final solution of the optimized parameters and their confidence interval. So here, for example, we created a command script that tells Bentson that to run the first to optimize the first model, then import the value from the first model and calculate the W by running the second model, and after that just import the W from the calc W model and just do another optimization to get the second to do another optimization on second step model, Finally, export the values to the confidence values of unknown parameters to the confidence interval, and just calculate the confidence interval. So using such a system, using such a command script system, we can just do like just gives Bentson one command, and it will just do the whole process of series of models one after each other, and do the whole things together, and just gives us the final parameters, value and their confidence interval. So that was it. Thank you so much for watching.